Welcome to class 20. We'll continue with continuous time stochastic process, inter-event times. Remember we talked about Poisson process. So if the events come in accordance to a Poisson process, then the waiting times should follow all T0 from 0 to 1, the time to the first claim, T1 is the time to the second claim. These will follow exponential distributions. Now if you see this diagram, there was no claim till this claim. T0 is time to the first claim. So time to the first claim is T0, that this time and this time, if you see, this is the first claim, you can say. This is another time T1 from here to here, then from here to here, from here to here. They are not same, not constant. So the distribution is not uniform. This follows an exponential distribution. It's like this. I am waiting to give a class and student will turn to the class. I will wait for the first student to come, and I don't know the spectators here, but I gave time 11 AM suppose. Then they will come one by one. I will wait. So my first waiting time will be when first student will turn up here, and then second waiting time is not the whole time. Suppose this is the first guy who will come tomorrow and he is 2 minutes late to the class, and this guy is 5 minutes late to the class, but T1 will be 3. T1 will not be 5 here. T1 is the time between this guy and this guy. Okay, that way. That's why we say inter-event times. If you see here, inter-event times, that means the time gaps, you can say. This time is T1. The whole time, if you see 5, that will be T0 plus T1. That is 5. So the times, they will follow exponential distribution. T0, T1, T2 is a sequence of independent exponential random variables, each with parameter lambda. That means we have to prove that all these variables T0, T1, T2, they will follow exponential distribution with this parameter, the rate parameter. This lambda has link with this one here, this one here, T0, T1, T2, NT. Okay, lambda I can write here. NT is a Poisson process. I can write rate lambda, or the occurrences are lambda constant with constant parameter, that is lambda. Whatever way you say, you just can write rate lambda. Suppose you get 50 claims a day, lambda will be 50. So that parameter comes here. Exponential lambda. So we can prove all this. If you see the previous syllabus, we had proofs of all, but now we will prove for one after 2019, and these are no more there. Although they are the same, there is no difference. They are similar, almost similar. Remember, we are not in stochastic process. We are considering a particular stochastic process, that is Poisson process. If this is stochastic process, this is Poisson process. Now we will go here to general stochastic process, Markov process. Okay, we are talking about Markov process. So Markov, will go to Markov process, and here for Markov process we are saying the waiting time follows exponential. This is different from this. Even the proof is not there in course this time. Okay, the proof it was there before. Here we are proving for a Poisson process. So from Poisson process we will go to a general stochastic process, which is a Markov process. Here we are considering only Markov processes. So Poisson process, it's only one part, one kind of whole set of stochastic processes. So this we can prove using Poisson process properties, but this one is for the whole stochastic process. So from particular we are going to there is always a confusion between this one and the last one. This is general result. We are talking about all kind of stochastic processes. The Markov process is here. This and this, they mean the same. I already discussed this one in the last class. Now coming to this one, we have a small proof here. T0 follows exponential distribution with parameter lambda. For that we have to prove the density function should be lambda e power minus lambda t here. Okay, this is what we need to prove. For that, because this one will get from this one, we'll try to differentiate. We'll try to differentiate this one, capital F T T0, and we'll prove that this is actually e power minus lambda t. If you differentiate this one, then you will get this one. Okay, it will be in fact this. Now you differentiate this one, differentiation of 1 is 0. This minus minus they will get cancelled, and lambda minus lambda will come here, lambda e power minus lambda t. Okay, this one is nothing but this one. If you differentiate the distribution function, you will get the density function. So this is what we want to prove, and then we can say, because the density function is lambda e power minus lambda t, T0 will follow exponential lambda. So now you need to prove this one. From this automatically we'll get this result. Now let's try to prove this one only from this one. So let me write capital T Ft, that is probability. Let me write the random variable as well. T0, the time to the first claim, T0 less than or equal to T, that is probability 1 minus probability T0 greater than T, that is equal to 1 minus probability. This is the only step you need to follow. Okay, so when we say T0 is greater than T, that means the waiting time to the first claim. See, this is our stochastic process. Let me write here only, or maybe we'll write here. Stochastic process starts at 0. There is no student in the class now, and then what will happen, the waiting time. This is 0. At 0, we are at 0. Now when one claim will come, it will go to 1. Stochastic process is at 1. That means one student entered the classroom. We don't know this time, and we know that this will follow exponential distribution, but that's what we are proving here. But we don't know this time now. So T naught is greater than T. That means this is T naught. This is T naught. T naught greater than T. That means suppose T is here, then T naught will be greater than T, because this is small t, this is capital T naught. So small t, capital T naught is greater than small t. That means up to small time t, the value is 0, because the waiting time, we know that it's T naught, the waiting time is T naught, and if you consider any time t before, nobody has arrived by that time. Suppose I say someone, and I say that I already waited 5 minutes and nobody came till now. That means my waiting time is T naught, that is 5 minutes, and before 5 minutes the class is empty, because my waiting time is more than 5 minutes. If my waiting time to the first student is more than 5 minutes, is equal to 5 minutes, my waiting time, before 5 minutes the class will be empty, but after 5 minutes one guy will be there, one student will be there after 5 minutes. Okay, maybe 5.1, if you check, there will be 1. So if this is T naught, before T naught nobody entered. Or otherwise also we can say, what is the chance that T naught will exceed T? What is the chance that I am now finding? What is the probability that my waiting time will be more than T? My waiting time will be more than T when till time T nobody enters. That means here N0 is equal to 0. Here Nt should also be equal to 0. Nt naught will be equal to 1. Now one student arrived, entered. So this is the only step we need to understand here. That is equivalent to probability Nt by time t also nobody arrived. That means Nt is equal to 0. Now we know the distribution of Nt. Nt will follow exponential lambda t, because Nt is a Poisson process with rate lambda. By time t you will have lambda t, right? Nt follows exponential distribution with parameter lambda t. So we'll apply this one. Now Nt is a random variable, so Nt follows this. Probability Nt is equal to x, or whatever you write, e minus lambda, means Nt here lambda power 0 x divided by x factorial. And when we find 0, you put 0 here, this will be 0, this will be 0, so that will be e power minus lambda t, because this becomes 1, this is 1. This is what we wanted. And once you get capital Ft, you differentiate. Here we got, and differentiate and get this one. That's all. This is a 3-line proof. The only thing you need to understand here is this step. That's all. Now let's go to a general stochastic process, the Markov process here. Here also the waiting time Wi, we are talking about the ith state. Okay, so if we have so many states, and if you talk about the ith state, what will happen is, this is continuous time, so the process will continue till transiting to a new state. So this is called waiting time. This time is called waiting time. First time it's making a transition to another state, not necessarily the second one. It could be anywhere. We are not talking about Poisson process or something like that. It can go here also. We are talking about transition. Then after some time it will come here, suppose. So this will be T1. This will be T0. Okay. So we can even write this way. Suppose this is waiting time, and then it makes a transition. This time is very small though, to here. Then it stays some time. It comes here. Then it stays some time. It goes there, that way. So these are the times. Okay. This time is very small. This is 1 instant. Okay. This is also very small. If you want, you can write like this also. Here only. Here making a transition. Then from here making a transition like this. Anyway, these will follow exponential distributions. So if you find greater than, then you will get this one. Now there is a very important concept we'll do today. Before that, you remember this one. Given that a time homogeneous Markov jump process is currently in state I, the probability that it will move to j, from I to j, when it leaves state I, that will be equal to mu ij divided by lambda I. This is a very, very important result. Okay. Once it will leave I, what is the probability that it will go to j? That means, suppose I am giving a class. Once I leave the class, where I will go? Maybe I will go to see a movie, or I will go to kitchen to cook something, or to make a cup of coffee, or maybe I will go outside to purchase something from the market. There are so many states. So once I leave this state, the state is now I am giving a class where I will go. So that probability is given by mu ij divided by lambda I.